Hello everyone. In a previous tutorial, we saw how to establish Modbus RTU communication with our Raspberry Pi here, running Codesys Control for Raspberry Pi and a remote Modbus RTU server. And in that scenario, the communication on the Raspberry Pi side here was done over USB. Basically, what we had is we had this RS-232 to USB converter. So you see we have the RS-232 coming in from here from our remote server, and the USB here that then we plugged into the Raspberry Pi here, and then we were able to establish that serial communication over the USB here. So a number of requests came in, and a lot of people were interested in how to do the same, but now this time instead of using the USB interface for the serial communication, we would use the onboard or the GPIO serial pins here, as you can see. So this GPIO header has different pins on which you can establish serial communication and therefore Modbus RTU communication. So the goal of this video today is to show and demonstrate how we can use the GPIO serial pins to establish Modbus RTU communication with a remote server or client if our Raspberry Pi was the server. So that is what we're going to do today. Okay, so before we proceed any further, let us just try to understand a little bit on how the serial ports on the Raspberry Pi actually work in general. So Raspberry Pis have at least two serial ports. They have multiple depending on the version or model of Pi you're using. For example, the 3B that I'm using here has two serial ports. One is the primary and one is the secondary. So if I pull up the Raspberry Pi pinout diagram here, you can see that on pin 14 and 15, these two pins would be used for the primary port. So the primary port connects via this pin 14 and pin 15. So 14 is the TX for sending out data, and then 15 is the RX for receiving data. So the primary here connects to those pins like you've seen, and then the secondary connects, is used by Bluetooth. So that is those are the two pins. Other models, of course, have more than two ports, but for the 3B that I'm using here, it only has these two, primary and secondary here. Now, each of those ports is driven by a UART. And on the Raspberry Pi, there are at least two UARTs. So if you have at least two ports, then that means you have at least two UARTs. The 3B again has two UARTs. So this UART 0 and then UART 1. And depending on the configuration that you have, one UART will be connected to either the primary or the secondary and vice versa. So for example, here, you can see the different models of the Raspberry Pi. We can concentrate on the 3B here because that's the one that I'm using. If you have Bluetooth enabled, then UART 0 would be reassigned to Bluetooth. And then UART 1 would be reassigned to primary. So if I have Bluetooth enabled on my Raspberry Pi right now, UART 0 will be assigned to Bluetooth, and then UART 1 would be assigned to primary. Remember, primary port is the one that connects to those two pins there. Okay. Now, it's also important to know the difference between these UARTs, UART 0 and UART 1. You would ask, why does it matter? So apparently, there are two types of UARTs. So there is this, the one that is called the PL011, and then there is one that is called the mini UART. So you either have the PL011 or the mini UART. Now, the trouble is that this mini UART has limited functionality. So you don't want to use it for things like serial communication. So that means that if we are to do serial communication, we definitely want to use this PL011. Now, here's the trouble. From the table here, you can see that UART 0 is this PL001 type, and then UART 1 is this mini UART. right? So that means if we go back to our logic here, if we have Bluetooth enabled, that means Bluetooth is using this UART0, which is the PL011. And then our primary is using UART1, which is this mini UART. That's something we don't want. We would want to have PL011 on primary, and then mini UART on Bluetooth, or we don't care anymore. As long as we have PL011 on primary, that's all we care about. Now, by default, UART0 is enabled on the Raspberry Pi. And therefore, if you have Bluetooth enabled, that means UART0 is enabled and connected to Bluetooth. Now, how can we reassign PL011 and therefore UART0 on our primary? So we can do two things. We can either disable Bluetooth, and therefore UART0 is reassigned to primary, or we can manually assign UART1 to Bluetooth and then have UART0 on primary. So that's the two options that we have. So either disable Bluetooth, and therefore you have UART0 on primary, or reassign UART1 manually on Bluetooth and then have UART0 on primary. So that is the whole concept here. So to recap, Raspberry Pi has at least two serial ports, primary and secondary. Primary connects via the GPIO pins 14 and 15, and secondary is used by Bluetooth. And then each port is driven by a UART, and there are at least two UARTs, UART0 and UART1. If Bluetooth is enabled, then UART0 is connected to Bluetooth, and then UART1 is connected to primary. UART0 is of type PL011, and UART1 is of type mini UART, which has limited features. And we want to have UART0 on primary, and therefore we can do two things. We can either disable Bluetooth and then use UART0 on primary, or we reassign Bluetooth on UART1 and then we use UART0 on primary. Okay. So for our case today here, we are just going to reassign UART1 on Bluetooth and then have UART0 on primary. So what you want to do is you want to log into your Raspberry Pi. So SSH into my Raspberry Pi here, 192.168.137, password. Okay, first thing you want to do is you want to enable the serial interface. So to do that, you write sudo rust-config, and then you want to go to interface options, and then you want to go to serial port, and then it will tell you, would you like a login share to be accessible over serial? And you say yes, and then serial login shell is enabled, serial interface is enabled as well, and then you click OK, and then you finish, and then you reboot your Raspberry Pi. Now, after your Raspberry Pi has rebooted, then you log back in. And we want to edit one file. So you want to edit this config file. It's under boot firmware config.txt. You want to scroll down here and here, and you assign mini UART to Bluetooth. So you just say DT overlay equals mini UART dash Bluetooth. So you've enabled UART, and then you reassign UART to Bluetooth. And then you save that, and then we are done with that. So we've enabled our serial interface, and we have reassigned mini UART to Bluetooth. Now to confirm that UART0 now is connected to primary, you can run ls-l/dave. And if you scroll up here, you should see that serial 0 is pointing to TTYAM0. Serial 0 means primary, and that is TTYAM0 is UART 0 there. So if you have that, then you know that everything is set up correctly. Now, after that step, now you can go ahead and make your connection. So what you want to do is identify your TX pin rather, and RX pin. TX pin is 14, and RX is pin 15. Now there is one more dilemma that we have to overcome, and that is regarding the physical layer for this serial communication. So the Raspberry Pi and many other microcontroller class devices use what we call a TTL voltage level for serial communication. So that translates to transistor logic. So TTL is a 3.3 to 5 volt level there for serial communication. And yet many other devices use RS-232, RS-485, which are levels way higher than what the Raspberry Pi can support. So that means that you cannot connect RS-232 or RS-485 directly to a Raspberry Pi because the level is so high. You would basically just ban the Raspberry Pi. I have made a small comparison here just to demonstrate how the two levels differ. So you can see that on top we have the RS-232, and then on the bottom here we have the TTL levels. So RS-232 usually ranges from plus 13 volts to minus 13 volts. 13 volts plus 13 volts is the logic 0, and then minus 13 volts is the logic 1. And TTL, like we said, is 3 to 5 volts. So the logic 1 is 3.3 or 5 volts, and then the logic 0 is 0 volts. So you can see that these are two incompatible voltage levels. So you cannot just hook up this RS-232 directly to the Raspberry Pi pins there, the RX and TX pins. Otherwise, you're just gonna see some smoke definitely coming out of your setup there. So to overcome this, we should convert this RS-232 voltage level to the TTL voltage level. And then we should then have our serial communication established in that way. So how do we do that? So there are multiple voltage converters that you can use. For this demonstration, I'll be using this SEED RS-232 to TTL converter. So it's a converter which has on one side a D9 connector, and on this side it has 4 pins. So basically what you do is this side here connects to the Raspberry Pi pins, and then this side here connects to the lead that is coming from the remote device that is driving RS-232. In fact, there are other converters that would convert RS-485 if you were using that. But for this demonstration, our remote device will be using RS-232. So we convert that communication, that voltage level, to correspond to what the Raspberry Pi can support. So like we said, on this side, we have the Raspberry Pi connection. So on pin 1, we connect ground. On pin 2, we connect VCC. So 3.35 or 5 for that case. And then you have TX and RX. So the TX would connect to the RX pin on the Raspberry Pi, and then the RX would connect on the TX pin on the Raspberry Pi. And then on this side, you have your 232 connection as normal. So you have this RX propagates through and connects to the RX lead of the RS-232. And then the TX as well propagates and connects to the lead that is for the lead of the RS-232 that is coming in on this D9 connector. So you just need to identify the pins, which pin is RX on this D9, which pin is TX, and then you just make your connection normally. So that is the converter we're using here, and this should do for us the job. So I'll show you what I have here. So this is my RS-232 to TTL converter. You can see the D9 connector on this side there. And then the 4 pins, like we said, ground, VCC, then RX, and then TX. And then on this D9 connector, we just have to identify from the datasheet of this converter, you can identify which pin is RX, which pin is TX, and then you can connect those respectively on the remote device there. So here we have RS-232, here we have TTL, and we've done the conversion. Then I've done the same thing here. So I have VCC, which is 3.3. I have my ground, I have my TX, I have my RX there. And basically, that's how the connection works. And now we can proceed to the remaining part. And that is the editing the Codesys user config file in order to access the serial ports from the Codesys world. From the Codesys world. So for that, we want to log back in the Raspberry Pi, and there. So we want to edit this Codesys Control _ user.config. So it's under etc Codesys Control and then Codesys Control _ user config. So to edit that, you want to go under syscom. So you can see syscom here. Remember, in the first tutorial, we used the USB interface for the serial communication. That's why we have on this line, we have linux.devicefile.1. So 1 means COM port 1. So you're assigning that interface as COM port 1. And then we specified that USB device. So you can see it from here. This is the TTY SEM0. And now for the primary serial port there, we use this TTYM0 there. So we say linux.devicefile.2, meaning we are sending it as COM port 2, and then /dev/TTYAM0. And that's it. That's all we need to do. And then you save the file, reboot your Raspberry Pi, and now you're good to go. So what we're going to do for the test, at least, let's just test this out and make sure that it's working. I have my RS-232 to USB here. So since I have RS-232 on this side here, I can just hook this up like this. Okay. Then I should connect this to my computer over USB there. And I should have communication from my computer to the Raspberry Pi. So serial pins from the Raspberry Pi to the converter here. Converter converts TTL to RS-232, and then I have this converter RS-232 to USB that will go to my computer here, and then I should be able to have serial communication between my computer and the Raspberry Pi there. And then later in a separate video, we shall see how we can just make this connection directly to our ABB PLC there. But for the test, at least, we're going to use just this converter here to USB, and then make sure that things are working. So I'll plug this into my computer, and then I'll open up this Codesys program that we already had before. So what I'll do is I'll create a simple Modbus server here on the Raspberry Pi. So I'm using Codesys Control for Raspberry Pi MCSL. So I'll just come here, add a new COM port, come at device, and then under field buses, I got under Modbus, and then select Modbus serial port and select this Modbus COM. Close this. Here's my COM port. I'll configure that first. So the COM port, remember we said we are using, so it's COM port 2. So I'll set this to 2. I'll set my communication parameters here. So I'll use 19,200. I use parity none. 8 stop bits, 8 data bits, 1 stop bit, and that should do it. And then on this, I'll add a server. Again, add device, and then under field buses, Modbus, and then Modbus serial device, and then I want to add this Modbus serial device here. So that's the Modbus server. Okay. Close that again. I'll configure my server. So I want 10 holding registers, 10 input registers. No coils, no discrete inputs. Unit ID is 1. I'll leave it at that. And then I want to create at least one variable that I'll map to one of these registers so that I can write that variable from my computer. So I'll come here in my main program unit. And I have a few lines of code here. I'll add another. This is a local Modbus server. So I'll just add one variable here. I'll just call it mod server data, maybe of type word. And then I'll go back here. I'll do the mapping. So I want to map it on the first register here, first holding register. So just double click, browse, and then attach or map that variable there. Okay, that's done. And now I can upload this program. So before I do that, I go to Tools, Deploy Control, enter my Raspberry Pi IP address, username, and SSH username and password. Connect. I want to make sure that the runtime is running. If it's not running, then I can start it, and then upload the program. Okay, status connected. Deployment, I can see all the installed packages that I have here, but I want to go under operations. So here's my runtime. Right now it's saying that it's running. If it was stopped, then I would have to run it from here. So remember, with if you don't have a license already for Codesys Control for Raspberry Pi, this runtime will run for 2 hours and then it will stop. So you have to restart it. So the trial license runs for 2 hours and then stops. So you have to restart it after every 2 hours. But now mine is running already, so everything is looking good here. Now all I need to do is upload my code. So come here, scan network, select my Raspberry Pi there, enter device management, username and password. Okay, log in and then upload my code there. Now I've created a server here on the Raspberry Pi, and I'm going to use a Modbus Master to write data to this server. Modbus Master Simulator, I would say. So I have a Modbus Master Simulator here, and I'm going to use this to write data to the server here. So I need to set the same properties like the ones that I've set here with this server here. So come to serial here, Modbus RTU settings. COM port is 3, so when I plug this guy into my laptop here, it will appear as port 3. COM port 3, bound rate, data bits 8, stop bits 1, and parity none. And then OK. And then I establish connection. And then if I come here, so this is the variable that I map to register 0 there. So if I want to write that variable, I'll come here, select write multiple registers. I have up to 10 holding registers, so I can write all of them. And I can now attempt to write data. So we can set 10 registers here. And then we start to scan. And if I open this here, so you can now start changing data, and you should see that as I change data, it should reflect right away in our variable here. So 200, now we have 200. Change it to 500, have 500, change it to 1000, have 1000, and we can set all the other variables as well. Okay, 0, 0. It keeps dropping a bit, but I think that could be that I have loose connections. But it's working. Basically, I can just set this to 100. And you can see from here the blinking light. So it shows that has been transmitted there. So it blinks on the converter here, RS-232 to USB converter, and it also blinks on the RS-232 to TTL converter there. My connection should be, I think, loose or something, because it keeps dropping a bit every now and then. But for the most part, it's working. I can try to troubleshoot the connection later. But for the most part, it works. It drops here and there. But for the most part, it's working. That's the most important thing. Yeah, it keeps dropping a bit, but I'll have to check that later. But yeah, you can see that if I set 50, okay, before it dropped 20, Yeah, 20 there, 40, 40 there, 80. Yeah, it keeps dropping every now and then, but so you can see total packets sent is 151, errors 17. So it drops packets here and there, but that shouldn't be. We can troubleshoot and check the connections and make sure that the connections are not loose or anything like that. But it's basically it's working. So yes, so for the next tutorial, I think we shall attempt to make this connection directly to the ABB controller there and test it out. But for the most part, it's working. So that is good news. So I think that's it for this tutorial. In the next tutorial, we shall see how we can make the connection directly to the PLC there, and then try to read and write data from the PLC there. Okay, so that's it for this tutorial. Thank you and have a nice day.